This is the 38th lecture. We take an example of digital to digital transformation and then enter into the domain of FIR design. In the last lecture, we had taken an example of an IIR band stop filter design and then talked about digital to digital frequency transformation. We showed that these transformations can be derived in a very simple manner if you know the analog transformations. As an example of application of digital to digital transformation, we consider this low pass filter. The specification of a digital low pass filter is the following. Magnitude, this is to be our prototype filter which we shall transform to various other kinds of filter. This is 0, magnitude in decibel, 0, -3, and then you have stop band. Well, the pass band age is 2.25 kilohertz. This is how specifications are given. Actual frequency you have to convert to normalized digital frequency before you start designing. Then this is pretty stiff, 2.5 kilohertz, and the sampling frequency f sub t is given as 9 kilohertz, and therefore the end of the baseband is 4.5 kilohertz. And you also notice that in terms of omega, this corresponds to 4.5 kilohertz corresponds to pi. So this is pi by 2, just to keep life simple. Okay, and 2.5 kilohertz corresponds to 2.5 pi divided by 4.5. Agreed? So this is equal to 5 by 8, 5 by 9. Yes, okay, 5 pi by 9. How much is that? Well, let's say 5 pi by 9. Let's keep it like this. Pardon me? 0.55. Let's keep it like this as long as we can. Okay. By the usual, pardon me? Oh, delta S is 10 dB minus 10. Yes, this is what we require. By the usual procedure, that is, we find out the normalized analog filter, then we make the analog digital, analog normalized filter to digital low pass filter. Okay, the transformation, the bilinear transformation, and get a transfer function which satisfies these specs as the following. This will be our prototype. We are going to exemplify the digital to digital transformation. So the variable should now be variable capital Z. We are going to go from capital Z to small z. So the variable, do not make a mess by assuming this to be small z, then you do not know what the new variable is. So our prototype, the filter that we start from, in analog case also the complex frequency variable was taken as capital S, from capital S to small s. So from capital Z we shall go to small z for other kinds of filters, and the this design becomes a third order, and we attempted Chebyshev. The design is 0.9027 up to 4 places of decimal, 1 plus z inverse whole cubed. That is how it shows. Does it show a low pass filter? Yes, because at z equal to minus 1, it will be equal to 0. Then in the denominator we have 1 minus 0.6906 z inverse plus 0.8019 z to the minus 2 minus 0.3892 z to the minus 3. This is what we get as the prototype filter, where I have made a mistake. On the right hand side, all z's should be capital Z. This is what we shall replace by another function of small z, which is a all pass function. Now,
sir, up to this, it is provided in the data sheets, or it is given to us.
This is given to us. Pardon me?
This transformation is given to us.
Which transformation?
This transfer function.
This transfer function, either it is given to you or you have to find it out. Okay? Or you have to find it out. That we have done many times, how to design a low pass digital filter. So this is not a problem, but this is our prototype. From this we shall derive other kinds of filters. I want to illustrate the digital to digital transformation. So I didn't write the intermediate steps, okay? By the usual procedure, this is what is done. Yes. You have to derive it.
Sorry, we are deriving, then why we are, what is the advantage of digital to digital transformation?
Oh, what is the advantage? Well, we showed these two alternative routes. One is, okay, two alternatives. One is you can go from digital specs to analog specs, then to an analog low pass filter normalized, then transform it to analog other kind, then put bilinear. You interchange these two steps here. That is, from the normalized analog filter you apply bilinear transform. So you get a low pass digital filter whose omega p prime, which is not normalized, omega p prime is something which comes. Then you apply digital to digital transform. So this is the alternative route. Advantage is that if you have a standard, if you have standardized this filter, then you can obtain any other kind of filter with the same tolerances without going through the process of analog filter again. That is, you simply replace capital Z inverse by the function of small z inverse. That is the advantage. Okay, now can we proceed? Let us say we design three filters. First, let us say we require a high pass filter, a digital high pass filter HP of Z with cutoff at 3.6 kilohertz cutoff, all right, which means that, recall that omega p prime for the low pass filter, it is equal to pi by 2, agreed? Omega p prime was equal to pi by 2. Here omega p obviously is 3.6 divided by 4.5 multiplied by pi, which is equal to 0.8 pi, no truncation, 0.8 pi, all right. Therefore, our transformation from low pass to high pass, as we know, is cap Z inverse equal to minus Z inverse minus alpha divided by 1 minus alpha Z inverse, where the only parameter to be calculated is alpha, and alpha is cosine of omega p prime plus omega p divided by 2 divided by cosine of omega p prime minus omega p divided by 2. And in this case omega p prime is 0.5 pi, agreed, pi by 2, and omega p is 0.8 pi, and therefore this becomes cosine of 1.3 divided by 2, that is 0.6 0.65 pi divided by 0.8 minus 0.5, 0.3 divided by 2 is 0.15 pi, and since this angle is greater than, since this angle is in the second quadrant, cosine shall be negative, and therefore the result is alpha is minus 0.5095. I kept up to 4 places, and therefore all that you have to do now is take capital H of capital Z and put Z inverse HP of Z inverse equal to capital H of Z, I beg your pardon, capital Z under the condition capital Z inverse equal to minus small z inverse minus alpha, but alpha itself is positive. So, plus 0.5095 divided by 1 plus 0.5095 z inverse, and the result comes as 0.0066 1 minus z inverse whole cubed divided by 1 plus 2.3605 z inverse plus 2.1018 z to the minus 2 plus 0.6884 z to the minus 3. Before I make a comment on this, I would like to show you what our prototype filter response is like. It's a Chebyshev filter. We started from capital Z capital H of capital Z. The response is this, response of the prototype filter. There are 3 different responses. Minimum order is 3 poles, and that is shown by the rectangles. That is, you see the equal ripple in the pass band, minus 3 dB corresponds to 0.707. So, the lower line is here, the upper line is here. For 3, there are 3 peaks and dips. On the other hand, for 5, the number of oscillations increases. 7, it still increases. What is the argument in favor of drawing this picture? I mean, what do we want to illustrate? We want to illustrate the following: that if we increase the order, we satisfy the stop band we over satisfy the stop band, okay? Whereas 3 may be just enough, unless capital N sub C was something like 2.1 or 2.2. Suppose it is 2.9 or 2.99, then it's worth seeing what happens if we increase the order by 1 more. Now, all of them are odd orders, so that all of them start from here to be able to compare, okay? All of them start from here, and you see 5th and 7th order, that is, we increase the cost provided we want better stop band rejection, okay? It's just out of curiosity that 5th order and 7th order responses have also been plotted. No change in the pass band tolerance. It is only the stop band that we over satisfy. Pass band is sacred. You also see the number of ripples increases as the order increases, okay? Now, about this filter, I shall show the magnitude response a little later, but there are several things to notice. One is this a high pass filter? It is. Is it indeed a high pass? Yes, it is, because at z equal to 1, it is 0. Now, how does 1 minus z inverse whole cubed come? You see our the numerator, how does this quantity come? Our numerator was 1 plus z inverse, 1 plus capital Z inverse whole cubed. How did this convert to this. This is also interesting. This happens because the transformation is an all pass function. 1 plus capital Z inverse would be 1 minus small z inverse minus alpha divided by 1 minus alpha z inverse. Agreed? And therefore, this is equal to 1 minus alpha z inverse. Now, what do you get? 1 minus alpha z inverse minus z inverse plus alpha. So, the numerator can be written as 1 plus alpha multiplied by 1 minus z inverse. And when you raise it to the power 3, the numerator becomes 1 plus z inverse to the power 3. It is a property of the digital to digital transformation, and this property is a reflection of the all pass nature of the transformation. Because capital Z inverse to small z inverse is all pass, this is what will happen. For example, in a band pass filter, it will be 1 minus, yes, the numerator would be 1 minus z to the minus 2, and because it is third order, it will be raised to the power 3. In a band stop filter, you can't say this. Okay? Band stop is rejection at some intermediate frequency. So, it would be slightly more complicated. Okay. It is good to examine every result critically, whether you have made a mistake or not, whether what you are expecting has been met or not. You can also verify that when Z inverse in this high pass function, when Z inverse equal to minus 1, the transfer function should be equal to high pass. At omega equal to pi, z small z inverse would be equal to minus 1. So, when you put small z inverse equal to minus 1, the result should be equal to 1. It may not come exactly 1 because of truncation in the fourth order. It will not. It will not. In all probability, it will deviate. Now, let us look at a bandpass design. Suppose it is required to go from capital Z inverse to small z inverse, where this is a bandpass filter with cutoff at 3.8 kilohertz upper cutoff and 3.4 kilohertz. The tolerances are the same as the prototype. Now, please notice that we are not touching the stop band at all. Whatever stop band edges come has to be accepted. Digital to digital transformation may not always work, because by transformation you may not get the desired stop band. We are hoping that this will be met, all right. Then only digital to digital transformation is useful, not otherwise, because we are not touching the stop band. Agreed?
So, it may be possible that it may undersatisfy the stop band.
That's right. Then you cannot use this.
So, then what is the method of checking it that it is satisfying or not?
You have to plot. There is no other way. At the end of any design exercise in digital filters, you have to make a plot and see whether the specifications are met or not, because of too many steps where error may creep in, okay, and the maximum error creeps in because of truncation, and therefore you must satisfy. And digital to digital transformation, there is no guarantee that the new filter satisfies the stop band specifications, because the only specifications we are considering are the pass band edges. We are not considering, there is no way that we can take care of the stop band edges. Agreed? So, this is a limitation of digital to digital. On the other hand, the first route that we followed takes care of pass band as well as stop band. Okay. So, the first thing we do is we find out omega 2 and omega 1. We had agreed that we will not write small p. Omega 2 would be 3.8 pi divided by 4.5 let us keep it like this, and omega 1 would be 3.4 pi divided by 4.5. And then our transformation is capital Z inverse equal to minus, it is important to remember the signs, the negative sign occurs in high pass and also band pass. In low pass to low pass the sign is positive, low pass to band stop the sign is positive, and the expression is Z to the minus 2 minus twice alpha k divided by k plus 1 plus Z inverse plus k minus 1 by k plus 1, and the denominator is k minus 1 by k plus 1 Z to the minus 2 minus the same term in the denominator plus 1. Okay. So, we have to find out alpha and k to be able to find out these coefficients. Okay. First, alpha is the ratio of cosine of omega 2 plus omega 1 by 2 cosine of omega 2 minus omega 1 by 2, and this is the reason why we did not convert them to fractions, we did not convert them to decimal numbers, we keep them as fraction, because you have to add them and subtract them, then divide by 2. We shall convert them into decimal fractions only when we cannot keep them in fractions anymore. Okay? Due to the apprehension of quantization error creeping in and polluting the result. So, what we get here is 3.8 plus 3.4 is 7.2 divided by 2 is 3.6. 3.6 pi divided by 4.5 cosine, is that 0.8? That is right, cosine of 0.8 pi, and cosine of 0.2 pi divided by 4.5. Agreed? Okay. This you have no other alternative but to convert it into decimal fraction. So, you take cosine of, this is 0.8 pi, that is not too bad, divided by cosine of, this becomes 0.0, it becomes a recurring fraction. So, you take 0.444 as many as are permitted by the calculator multiplied by pi, and this comes out as minus 0.8170. This is significant. This 0 is significant. Why? It only tells you that the next digit is less than 5. You must follow this discipline. If you truncate at 4 places, you must truncate all the numbers, and even if it is 0, you must show it. Okay, this is alpha, and k, if you remember, cotangent of omega 2 minus omega 1 by 2, then tangent of omega p prime by 2, and omega p prime is pi by 2, so this is 1. So, this is simply cotangent of 0.0444 pi, and that is calculated as 7.1154. After you do this, the next step would be to calculate those constants, the coefficients. One of them is k minus 1 by k plus 1, and that calculates as 0.7536, and the other is twice alpha k divided by k plus 1, twice alpha k divided by k plus 1, this comes as minus 1.4326. It is advisable to write the transformation in specific form. The transformation therefore is Z inverse equal to minus, do not forget the minus sign. As many times as you write this, you will make friends with it. Z to the minus 2 plus 1.4326 Z inverse plus 0.7536 divided by 0.7536 z to the minus 2 plus z inverse remains the same plus 1. And if you substitute this in the expression, then you get h bp of z as equal to 0.123 4 zeros and 6. There is a problem here, isn't it? If we had truncated at the third place, then we would have got as 1, a gross error, 40% error. And if we had truncated the second place, it would have been 0. You see the menace of truncation error. Actually, 4 places, it is at this point that you discover that you should have kept more places, and that is why I always say keep as many decimal digits as are permitted by your calculator. Okay? And then as expected, we should have a factor of 1 minus z to the minus 2 whole to the power 3.
So on the left hand side we will get a capital Z inverse.
No, this is small z. This is equal to capital H of capital Z with z equal to this function. So in the denominator I get 1. I wanted you to notice this, that you have got a number. Similarly, there is no guarantee that other coefficients will not be affected like this. Whenever you get this, you go back, okay, and see that you have not made a proper judgment of the number of bits to be kept. Of course, in the final realization of the digital filter, you shall be dictated by the hardware or the cost that is available. A to D conversion, D to A conversion, they work on a certain number of bits. It is either 8, 16 or 32 power of 2. 1 plus 4.7200 Z inverse. You see what I mean? I should have kept more, otherwise 2 zeros would not have come, plus 10.2422 z to the minus 2 plus 12.7890 z to the minus 3, another 0 is coming, which only shows that keeping up to 4 places of decimals is a risky matter in this particular design. But we could not learn this lesson to start with. To start with, we did not know how many to keep. 12.7890, then the next one is 9.6874 z to the minus 4 plus 4.2226 z to the minus 5 plus 0.8465 z to the minus 6. Why is it 6th order? Because we transformed a 3rd order by a transformation which is not bilinear. If it was bilinear, then there would have been no change of the degree. Biquadratic, and that is why the degree is increased by a factor of 2. Finally, C. Let's design a band stop filter with edges at 3.6 kilohertz. Pass band edges, not stop band. Stop band we have no control, whatever comes we have to take. 3.6 kilohertz and 3.15 kilohertz. You know what is done is, if you have a standard design and you encounter a new design, then first you call this program back and try to design it by using the transformation. See if it satisfies. With MATLAB you have to wait for half a minute or so. The magnitude plot will come on the screen. You see whether you have satisfied it or not. If not, then the standard design that is available is not useful to you. You have to start afresh. Okay? Is it clear? We have no control over the stop band. Now 3.6 kilohertz, what does it correspond to? 0.8 pi. 3.15 kilohertz, I think I have made a mistake. how much does it correspond to? 3.15, 4.5 pi. How much is it equal to? It is 7 times 0.7. Ah, yes, okay. Numbers were chosen carefully. It is 0.7 pi. Agreed? And therefore, the transformation now is capital Z inverse equal to no negative sign, positive sign, z to the minus 2 minus 2 alpha divided by k plus 1 plus k. I will tell you why I write 1 plus k, because you will get 1 minus k, not k minus 1. In the previous case we wrote k minus 1. Okay, there is no k here, this is what is to be remembered. So, this multiplied by z inverse plus 1 minus k divided by 1 plus k, and the denominator would be 1 minus k by 1 plus k z to the minus 2 minus the same quantity plus 1. This is the transformation. So, we shall have to calculate alpha k and then these constants 2 alpha by 1 plus k, 1 minus k by 1 plus k. Alpha, the same formula as in the band pass case, that is cosine of alpha is cosine of omega 2 plus omega 1 divided by 2 divided by cosine of omega 2 minus omega 1 divided by 2, and this comes at cosine of 0.75 pi divided by cosine of 0.05 pi. This calculates to minus 0.7159. Then k, instead of cotangent, the only difference is we shall have a tangent. Tangent of 0.05 pi. The other quantity is tangent of pi by 4, that is 1. So, this comes as 0.1584, and under this condition 1 minus k divided by 1 plus k calculates to 0.7265, and twice alpha divided by 1 plus k becomes minus 1.2361. We must write the transformation with numerical values, because there is a negative sign. If you put by mistake a positive sign, then you are gone. There is a negative sign in the transformation also. Therefore, in order to avoid mistakes, we write the z inverse z to the minus 2, the sign would be plus 1.2361 z inverse plus 0.7265, then 0.7265 z to the minus 2 plus middle term is the same plus 1, and the transfer function of the band stop filter, when you put this in the low pass prototype, you get, unfortunately you do not get 1 plus z to the minus 2 or 1 minus z to the minus 2, because the focus is now on the stop band rejection, and we call this n of z by d of z. It is a long number. N of z is equal to 0.6013, 1 plus 4.2955 z inverse plus 9.1505 z to the minus 2 plus 11.5266 z to the minus 3 plus 9.1505 z to the minus 4 plus 4.2955 z to the minus. Do you notice something interesting? Symmetrical, linear phase. The numerator is linear phase, not the total filter, because the phase is affected by the denominator as well. Why did it come like this? Once again, it is also a reflection of the fact that the transformation is all pass. All pass property gave rise to 1 minus z inverse whole square, no, 1 minus z inverse in the denominator of high pass, 1 minus z to the minus 2 whole squared in the numerator of band pass, and it gives a linear phase here. Linear phase is a reflection of the interchange or the reversal of the coefficients in the all pass. Okay. These are points one would like to observe carefully. The denominator is 1 plus, unfortunately this does not happen in the denominator. You should not expect it either. If it happens, then you have a dangerous situation. What is it? No, not necessarily. The denominator, if the denominator is also a linear phase polynomial, then it is a dangerous situation. What is the danger? Where do the zeros of a linear phase polynomial lie? They lie in reciprocal pairs, and therefore you would have poles in magnitude z greater than 1 outside the unit circle, and the filter would have been unstable. Okay. So if you have obtained that, then you know you have made a gross mistake somewhere. Okay, 3.6462 z inverse plus 6.5164 z to the minus 2 plus 6.8307 z to the minus 3 plus 4.4205 z to the minus 4 plus 1.6247 z to the minus 5 plus 0.2750 z to the minus 6. This is what it is. It's a longest transfer function, but you see the sweat that you spend on designing a function like this, it's worth it, because your company they will not manufacture one such filter, they will manufacture maybe thousands of such filters, and you will spend as much time as possible on the design. Now this is not, it is not guaranteed this will satisfy the specs, so you will have to plot it and see whether it satisfies the specs or not. Okay, and this effort is worth spending, so that no catastrophe occurs at a later date.
So will every numerator of band stop filter will be a linear?
No, not necessarily.
It's just this case.
It is because we have transformed a prototype low pass filter to a digital band stop filter by using an all pass transformation. This is a reflection of it.
Using this digital to digital transformation, you will always get a
That is correct. That is correct. Now comes the question of their frequency responses. The three frequency responses are given here. A slightly peculiar way. You see, it is plotted not up to pi, but up to twice pi. Just to remind you that it is a periodic function and the magnitude is an even function. So what happens at pi on both sides, they should be identical. Okay. Again it will happen at pi, then 3 pi. This, for example, I have put this red mark to show that our base band, our interest is only up to this. You see, it is a digital Chebyshev, which our prototype was a Chebyshev filter, so there are ripples. Okay, and it is a third order. So 1, 2, 3 peaks and dips. High pass, then this is band pass, and these are the band edges. Center frequency is somewhere here, we do not care where it is. Similarly, this is a band stop, this is the stop band filter. We can find out what the center frequency is in both cases, because alpha is equal to cosine of omega naught. It happens. I would strongly urge you to prove that it is so. I have not done the proof. Okay, and it is at this point that we can go now to FIR design. Enough of IIR design. IIR design is very, you can do this design very confidently because your base was analytical base. Okay, everything was obtained in a closed form. FIR unfortunately is not so. In FIR there is a lot of uncertainty, and at every step you have to ask yourself, am I proceeding in the correct manner? Will this satisfy the specs? You start almost blindly in FIR. You see, in IIR there were analytical formulas for calculating the Butterworth order and Chebyshev order. There is nothing like this in FIR. In FIR you only have empirical formulas which may or may not work. If the empirical formula gives you an order of 17, you might have to use an order of 20 or 21. Empirical formulas always have this kind of tolerance, uncertainty. Even then, why should we use FIR? If the filter design is so uncertain that at every step you have to go back and ask yourself, am I proceeding in the correct direction? Have I taken the correct order? Have I taken the correct procedure? If that is so, then why should you use FIR at all? Unconditionally stable is one. Linear phase, that is the utmost, that is of utmost importance. If linear phase is a strict requirement, for example in data transmission, data processing, if a rectangular pulse becomes smeared because of delay distortion, then a rectangular pulse does not convey what you wish to convey. In speech processing, linear phase is a strict requirement. So you have to use two advantages. One is that it is linear phase, and the other is that it is unconditionally stable. There is a third advantage. You see, once if you have a non-causal FIR, then you can make it causal. How? By simply shifting the whole thing to the right. Isn't that right? That is, you multiply with the required number of delays. So realizability is not a problem. Realizability of an FIR filter is not a problem. Although it is not a great advantage, but since we are listing advantages, this is one of the advantages. The disadvantage is that you have to use for the same specs a large order. So the cost goes up. What can be done by second order may require a 28th or 30th order FIR. So the cost goes up. And number two, the implementation, if you implement it by convolution in the time domain, is very slow. Convolution is a slow process. If you write the software or do the required hardware, multiplication and addition and so on, it is a slow process. Nevertheless, this is not a disadvantage, because convolution can always be calculated by DFT. Agreed? If h of n and x of n you have to convolve, you take capital H of DFT k and capital X of k, multiply the two and then take the inverse DFT. DFT is also a slow process, you are not saving anything. FFT. That is why FFT is so popular. So FIR, the disadvantage of slowness or speed of processing being very slow can be overcome by using FFT. Okay. The design methods, semi-analytical methods, there are only two of them. Semi-analytical, because it is not exact. Like IIR, you cannot say with a degree of confidence that what I have designed is the most correct one. And there are two semi-analytical methods. One is the so-called windowing, and the other is frequency sampling. these two are semi-analytical, and then of course you have the computer aided design of optimal, so called optimal filters. They are also called minimax filters, minimax design, because in computer aided design procedure using Remez exchange algorithm, what you do is minimize the maximum error. That is the, you should at least know the term, why it is called minimax. Standard programs are available, they are very costly programs for design of FIR filters using computer aids, and such designs are called minimax designs because these designs minimizes the maximum error. Okay, they are also called optimal in that sense. We will concentrate on the semi-analytical designs. Often before you go to computer aided design, one uses windowing or frequency sampling to get a rough design, and then you polish this design with the help of a computer aided design, okay, procedure. Now the philosophies that are used are extremely simple. In windowing, for example, you have been given a desired transfer function, okay, a desired transfer function, and you know the transfer function is periodic with a period of twice pi, and any periodic function can be expanded in Fourier series. All right, any periodic function can be expanded in Fourier series. So what you do is you expand this into Fourier series e to the minus j n omega, n equal to 1 gives you the fundamental, okay, and there are some coefficients h d of n, these are the Fourier coefficients, then summation, and in general you have to go from minus infinity to plus infinity. Agreed? This is the Fourier series expansion, which is the same as the Fourier transform of the sequence h d n, and therefore h d n is the impulse response sequence. Agreed? So given a desired transfer function, and this is FIR, you will have not FIR. h d n shall be of infinite length in general. Agreed? But what you do is you first expand in Fourier series, and then you argue that this is IIR because h d n is of infinite length, and arbitrarily, this is where the uncertainty comes, arbitrarily you truncate it. You truncate maybe at n equal to minus n1 some number to n equal to plus n1, okay. Then the resulting sequence will be will define a finite impulse response of length twice n1 plus 1. Agreed? Now this filter is obviously not realizable because the impulse response is not 0 for n less than 0. Agreed? But the solution is very simple. You simply multiply the whole thing by z to the minus capital N1. Agreed? Simply multiply the resulting transfer function by z to the minus N1. Now there is no guarantee that you have satisfied these specs. This capital N1 is purely arbitrary to start with. Okay? There are empirical formulas to get you an idea of the order that you shall require. Okay? What we shall do is, instead of truncating from minus n1 to capital N1, we will truncate from 0 to some capital N minus 1. That is, what we will do is, we shall take an h of e to the j omega, which will be an approximation to h d of e to the j omega, and we shall take this as summation h d of n e to the minus j omega n, n equal to 0 to capital N minus 1. So that the length is capital N. Okay? We have thrown out all others. I want a realizable filter. So h of z would be simply equal to h dn z to the minus n summation. I have taken capital length equal to capital N, so it is a finite impulse response. We do not know beforehand what this capital N should be. So it is a guess, it is a guesswork. Fortunately for low pass filters, well, for any kind of filter, these people at Bell Labs, including Kaiser, Rebinar, Kaiser, Gold and so on, they investigated a very large number of filters on the computer. They made the designs and they came up with some simple empirical formulas for estimating the order that is needed given delta P and delta S. Given the tolerances in the pass band and stop band, there are some simple formulas for estimating the order. There are some complicated formulas also. If they require stiff, then there are some elaborate formulas also. Okay, we will come back to those formulas a little later, but these formulas were worked out not with the kind of tolerance scheme that we are following. What do we follow? Highest is 1, in the pass band lowest is delta P, and in the stop band highest is delta S. What, for historical reasons, I do not know why they used it like this. These empirical formulas that are given for a typical low pass filter, they use maximum as 1 plus delta 1, the minimum as 1 minus delta 1, and this is used as delta 2. The empirical formulas are in terms of delta 1 and delta 2, but converting from here to our specs, that is, we take this as 1, let me use a different color, we take this as 1 and this is delta P, and this we take as delta S. Converting from one spec to another is not a problem. All you have to do is to normalize this by dividing by 1 plus delta 1, okay, and therefore your delta P would be equal to 1 minus delta 1 by 1 plus delta 1, which gives you delta 1 in terms of delta P as 1 minus delta P divided by 1 plus delta P. Is that correct? Okay. And delta S would be equal to delta 2 by 1 plus delta 1. And since delta 1 has been found out, you could put this here, and the result is delta 2. Delta 2 also you have to express in terms of delta P and delta S, and this comes as 2 delta S, I hope I am right, divided by 1 plus delta P. So I want to point out right here delta P, correct. I want to point out right here that those formulas for estimation, because they are the only things that are available. You are in an ocean and you clutch anything for support. This is the only support that is available, and it required many hours of work on the computer by Bell Labs people to be able to come to this kind of a formula. It is the only thing that is available. So between the formulas and our convention, one has to remember this and this, that is all. When delta S and delta P are given, you have to find out the corresponding delta 1, delta 2, and then write the formula. And the formula is the following: capital N, the simplest formula is minus 10 log 10 delta 1 delta 2 minus 15, actually it is 14 point something, simplify. Anyway, there is a lot of uncertainty, so You could use round numbers and keep your life simple. Plus 1, that's also not very important. If this comes out as 300, then 300 plus 1 or 300 minus 1 is not a problem. Divide by 14. Now they used a quantity delta, where delta in our notation, delta 1, delta 2 I have already said, delta in our notation is omega s stop bandage minus pass bandage divided by twice pi. In other words, what they used was the frequency, actual frequency difference, the bandwidth. Well, we will not go into this because there is confusion between IIR, transformation, analog frequency and so on. We will stick to this, omega s minus omega p divided by 2 pi. You can substitute this here and perhaps cancel 1, 2 between 14 and 2. That's not important. But this is a gross estimate. Once you get this estimate, you can go ahead designing, but you must find out the actual response and see whether it satisfies or not. We will continue this next time.